Okay, so we started class example 26. Thank you very much. So we started class example 26, where we had a big reservoir and two different pipe size was added with that reservoir. So the question was, what was the total flow inside each pipe or final flow at point E? So what we did, we just started, we read the question and we named the pipe BD as pipe 1 and DE as pipe 2, and we tried to identify all the given values here. And we found that for this one, we have two cases. We need to solve two cases. The first one, we already know the friction factor. So you can imagine the part A will be a little bit easier because at least two unknowns are given. For part B, where the friction factor is not given, that means we need to do some extra steps to get the friction factor. Other than that, all the calculations will be same. Now, for this one, since we have more than one pipe size, we can call that as pipe system. And we need to identify at the very beginning whether these pipes are connected in series or in parallel. What do you think? They're connected in series or in parallel? They're connected one after another. So they are connected in series, right? Okay, so once we know that, that is kind of like 20% problem solved because we know what type of connections we have here. And that will give us two exclusive equations for this setup, because we know for pipes in series and parallel, we have, like, we know the hydraulics, how the total flow things work and how the total head loss we can calculate for each type of pipe system, right? So that's why it's important to identify the pipe connection. So we'll start from that point for today's class. So I will write down this statement at first. Pipes are connected in series, which is good. So we can say, since its pipes are connected in series, exclusive. Oh, and one more thing, this pipe class example 26, 27, that is not included in your test 4. Exclusive equations for series connection. So the very first one is, we know for series connection, the same flow is going through each pipe. So Q equals to Q1, Q2. So that is equation number 1. We also know the total head loss for the system is the summation for head loss of individual pipe, right? So I will write down that also. Since we will work from A to E, so I will write down the head loss A to E equals to head loss for pipe 1, head loss for pipe 2. That is equation number 2. Now those are two exclusive equations. We apart from these two equations, we also have the energy equation, we have the mass conservation, we have the momentum conservation. So we have 3 more equations here. Now, as I said, most of the time we will not use the momentum conservation equation here because we are not dealing with force, any force here. So we will, you will see we are using the energy conservation and the mass conservation. That makes, that gives us in total 4 equations for one single problem, which is good. So we will not be out of equations. That will be good. Okay, now that is the 2 equations. Now, once we know these equations, we need to calculate something, or we need to see how can we incorporate all the known values into these equations, right? So let's start with the energy equation. If we apply the energy equation between A and E, I know there will be a term for head loss, and then we can incorporate the equation 2 into that part, right? So let's start working with that one. Apply energy equation between A and E. The datum is already given, so we don't need to think about that. So the equation will be PA over gamma V square head loss A to E, right? Now we need to identify what values we already know and which values we can consider 0. Now in between A, oh, that should be E, not B. Everything should be E. Okay, so is there any pump or turbine in between A and E? No, so these two terms are already 0. Now, point A, that is on top of the reservoir, open reservoir, which is open to atmosphere. So the pressure is 0. And what about the velocity? The velocity is almost 0 because that is open to it's a big open reservoir, and with if you compare the velocity at A and E, maybe that will be 100 times higher than A. Sorry, 100 times lower than the velocity at E. So that will not make that much difference. Okay, what about PE? The pressure at E, it's open to atmosphere again, so it will give you 0. Now we know the datum, which is at E. So what will be the elevation head for A? What it will be? 13, because 3 plus 4 plus 6, right? So I will write down this way, 6 plus 4 plus 3. Okay. What about ZE? It will be 0. Okay. And HLAE, I don't know at this point. I will work on that. So finally, we have 13 equals to V square over 2G plus head loss AE, right? Now, we already named the pipe BD as pipe 1 and DE as pipe 2. That means the velocity at E is actually velocity 2, right? V2. So I will just rename this so that we don't have to deal, like we will not be confused with so many different velocities. Here, because VE equals to V2. Okay. That's why instead of VE square, I will write down that as V2. And I will name that equation as equation number 3. The reason I'm numbering all the equations, because you will see we already have 4 available equations, and like we will be so confused if we don't number that. So it's always easier to number the equation so that whenever we need something, we'll just refer that equation. Okay. Everyone's good up to this point? Okay. Now look at here. we don't know the head loss at this point, but we know the relation for the head loss for each pipe from equation 2. So why don't we use equation 2 into equation 3? That way we will know something. Okay, so let's start working on that. Insert equation 2 into equation 3. Okay, so that will give us 13 v2 square over 2g equals to 13 v2 square over 2g, head loss 1, head loss 2, right? Also, for each head loss, we know there can be major and minor both. So we need to look for both losses. If there is no minor losses, our life is a little bit easier. If there is minor losses, we just need to find out the sources. Okay. Okay. So let's work on that. v2 square over 2g, h major plus h minor for pipe 1, h major plus h minor for pipe 2. Okay. So 13 v2 square over 2g plus. Now for major head loss, we use the Darcy-Weisbach equation. So what we will do, F1 L1 D1 V1 square over 2g, that is the major head loss. For the minor head loss, summation of KL1 V1 square over 2g, right? For pipe 2, it's F2 L2 D2 V2 square over 2g, summation of KL2 V2 square over 2g, right? The next line is very important because next line we will input all the known values on this equation. So if I miss something, just stop me so that we can have the correct equation. Okay. So 13, I don't know anything about V2, so I will keep that as it is. Now, for part A, we know friction factor 1 and 2. And for part B, we don't know friction factor A and 1 and 2. So at this point, what I will do, until I get a small, like concise equation, I will keep F as F. Like I will not use the values here because for part B, I need to do lots of calculation. So at this point, I will just keep F as F, but I will add all the other known values here. Okay. What is the L1? What is the L1? Look carefully, 10 plus 4, yes. And we know the diameter, which was 6 inches, that means 0.5. Okay. And since I have V1 square over 2g, V1 square over 2g for both of these terms, what I will do, I will keep the V1 square over 2g outside of the parentheses, okay? And summation of K for minor loss for pipe 1, we decided, we got that, which is 1.4, right? So 1.4 V1 square over 2g, okay? I will keep F as it is. What is L? What is L2? It's 3 and D2 was 0.25 and summation of KL for pipe 2. It was 0.89. So V2 square over 2G. Are we good up to this point? Okay, good. So the next line will be just finding the values for L over D and everything. And are you seeing we have one more V2 square here? So what I will do, I will keep all the V2 square over 2G together. Okay. So if you're done with this slide, let me know. I will move to the next slide. Everyone's done? The back. Are you done with this slide? Okay. So we will have 13. What is 14 over 0.5? 28, right? 1.4. And what is 3 over 0.25? 12, right? Point 89 V2 square over 2G plus V2 square over 2G. So what I can write down, 28 F1 plus 1.4, 12 F2 0.89, and this one is V square over 2G. That means it is actually multiplied with 1, right? So I can write down 1 here. V2 square over 2G. So the next line is 13, 28 F1 plus 1.4, 12 F2 1.89 V2 square over 2G. Everyone, you got from where I got that one? Are you seeing that V square over 2G here? And we have two more terms like V square over 2G here. So if I want to keep all the V square over 2G, like for these three terms, what will it, do you know how to take common from three different terms if we have common things? So we have common what? V2 square over 2G, right? So we already had 12 F2 plus 0.89. But for this V square over 2G, what number we have? Just 1. When we don't have anything, that means we have 1, right? So that means 12 F2 plus 0.89 plus what? 1, right? You got that one? We had some difficulties in section 1 also, so just wanted to make sure that you know how did I get 1. Does that make sense? How did I get 1? Everyone? Okay. So now, how many unknowns we have here in this equation? If we consider we know the friction factors, we have 2 unknowns. And for part B, we have 4 unknowns in one single equation. Since we are working with part A now, so I will consider we have only 2 unknowns here. Before doing anything, I will name this equation as equation number 4. Okay. Now, that is the correct number, right? What was the last equation? Equation 3. Yes. Now, is there any way I can connect V1 and V2 and reduce at least 1 unknowns from this equation? Is there any way I can connect V1 and V2? From the given equations or given relation, do you think I can connect V1 and V2? The Q, yes. So since the same Q is going into pipe 1 and pipe 2, I can say Q1 equals to Q2, which is that relation, right? Equation 1. Good. So that's what I will use. So what we will do, from using equation 1, we will try to reduce at least one unknown here. So from equation 1, Q1 equals to Q2, A1 V1, A2 V2, pi over 4 D1 square V1 V2. Can I cancel pi over 4 from both sides? Okay, so cancel this one, and then if I just move here, you can express V2 in terms of V1 or V1 in terms of V2. That doesn't matter. So I will just use V2. So D1 square, D2 square, V1. So D1 was 0.5 square, 0.25 square, V1. So what is that number? 0.5 square over 4. Okay. So 0.25, yeah, that should be 4. Okay, so finally we have V2 equals to 4 V1, and that is equation number 5. Now what should be the next step? What was the reason to work on this part? So that we can reduce at least one variable, right? So what we will do now, instead of this V2, we will use 4 V1, so that finally we'll have just one unknown. Okay, so let's do that. Insert equation 5 into equation 4. Okay, so we had 13 28 F1 1.4 V1 square over 2G. Now we have 192 F2 1.89 4 V1 square 2G. Right? Is that correct? Okay. So now if you can see here, now we have F1, F2 and only V1. We know the value of F1, F2, so we can solve V1. But before doing that, I will just polish this equation a little bit because it's just a very big equation. So 21F 1.4 V1 square over 2G. Since it's 4 square, 192, 4 square, 1.89. 4 square V1 square over 2G. Please check this equation if I missed anything or if that is the correct expression. Check this equation properly. Yes. Yes, that will change the whole thing. If it's multiplication form, that will be V1 to the power 4. Thank you for that. Other than that, did I miss anything here? Anything? 192, it was, that that is actually not 192. That should be 12. 12 okay. Multiplied with 16 is 192. I just did some calculation inside my brain. It should be 12. Yes. It's okay. Right now, all the things are correct. Good. Thank you for correcting those two errors. So I can write down the next line. Now I have everything in terms of V1 square over 2G. So what I can do, I can take everything inside the parentheses and keep V1 square over 2G on the other side, like outside of the parentheses, right? So 28 F1, 12 multiplied with 16 is, I think, 192, right? F2, 1.4. What is 1.89 multiplied with 16? Four square coming from? Yes, it's because of, if you look at this one, we had V2, right? And V2 equals to 4V1. So instead of V2, I use this one? No, here? There will be one friction factor, yes. That is correct. That should be 12 F2 then multiplied with. Now it's correct? Because I'm here I wrote down V1 square over 2G. So there is like 4 square here. So I just move. Yeah. So that I can keep only the V square over 2G. Okay, so what is 1.89 multiplied with 16? What is that number? Give me that number. .89 multiplied with 16. 3.24. Okay. Oh, 30.24. Okay. Okay. Now 13. 28 F1. 192 F2, 30.24 plus 1.4 is 31.64 V1 square over 2G, right? Now, since we are trying to find Q, which is like a function of velocity, so why don't I express this equation in terms of velocity? So that will be 13 multiplied. 28 F1, 192 F2. Okay. And I will name that equation as equation number 6. Okay. And our task is almost done. That was the hardest part, to get that expression. Now, for part A, you know the friction factor F1 and F2, right? So you can actually use that value in this equation and find the V1. And for part B, what we need to do? We don't know the F1 and F2. If the friction factor is unknown, the velocity is unknown, what? You need to guess and check. Like you need to guess one F value and find the value. But here we have two friction factors. So we need to work on two tables simultaneously. But let's complete part A first, okay? Up to this point, Did you get all the steps? I know it's long, but if you look at the like concept, it's just we work with different equation and replace one equation by other equation. Okay, and you don't need to follow the same sequence. You can start with q1 equals to q2 and then come to the other equation. There is no exact sequence. You can do anything as long as you are just using all the equations. Okay, now can you give me the velocity one value from equation 6? Velocity is what? 4.767. Okay, so I will just write down. That seems correct actually, because I got 4.78. 32.2. What was the friction factor? F 1.021, right? 192.024 plus 31.64. Okay, if you do all the calculation, you should get 4.78 feet per second. So that gives us V2 equals to what? 4 times. What is that one? 19 point something. Now, since our final objective was to calculate Q, technically you don't need to calculate the V2 here, because using V1 you can calculate the Q. But just to check your calculation, it's always good to calculate V2, and since we know Q1 equals to Q2, so what you can do, pi over 4.5 square multiplied with 4.78, and for Q2, pi over 4.25, 19.07. Now you should get the same number from both of these calculations. Even if you do the wrong calculation, still you should get same number. But it just reduces some of the possibilities of doing the wrong calculations. But you are not required to do the calculation for Q1 and Q2, because we need only one Q. But just for your own checking purpose, you can check both. And you should get the same number for Q1 and Q2. Give me the number. What number you got? One point 0.94. Okay. And for this one, the same. Okay. 0.94 feet cube per second. Feet cube per second, right? Great. If we get the same number, that is great. Can you just keep one and pass to others? Okay. So what we actually did here, at first we used all the exclusive equations, and then we connected those equations for the energy equation and the continuity equation, right? Now within few seconds you will get the solution for this class example 26A, and also for B. So for B, since we did the similar kind of problems already, what we will do, we'll just go through the steps with the solutions. Okay, so once you have this solution, just go to this page, like second page of that solution. What we will do for part B, we don't know the friction factors, right? So we will start from the equation 6. So equation 6 was V1 equals to 13 to 32.2. And we know when we don't know the friction factor and V, we need to do guess and check, trial error, or something like whatever you call that. So this time we have two friction factors. What we need to do? We need to guess for F1 and F2 both and you need to work on two tables simultaneously because in each equation you have F1 and F2. Okay, so what you need to do here, at first you will assume F1 and F2, then from equation 6 you will find V1, equation 5 you will find V2, Reynolds number epsilon over D, and from the Moody's diagram you will find friction factor for both cases. If its percent of difference is more than 5%, you will need to do one more trial. The same thing, it just double work you need to do, which is time consuming, but concept wise, it's the same thing. Okay, so you already have that here, solution B. So what I will do for the very last homework, I may ask you to work on this part just to make sure you understand what we did here. Okay. Now, I will just stop here for 1 minute and I will take questions from you about this one. Did you get the concept? Maybe not the whole calculation process, but did you get the concept for pipes in series? The same flow will go under each pipe. And as I said, you don't need to follow the same sequence how I did. You can follow any possible sequence. I don't mind as long as you use the main concept. Okay. Yes. How did I get 10 plus 4? That's because, are you seeing that from this point to this point it's 10? And since from B to D is actually pipe 1 and this one is 4, so that is actually 10 plus 4. That's why we use 10 plus 4. And they are connected in series also, but since they are the same diameter, we don't need to calculate separately. We can consider the same pipe. But the next pipe, since that one is different diameter, we need to do a little bit extra calculation. Yes. Because 10 is, yeah, 6 is the vertical distance. Okay. Any other question for this one? You are good, all of you? Okay, you will have one homework which will be due on maybe Monday during it. I don't know because that's the last day. So, or I will do something maybe Tuesday or something. So one homework, one question will be about pipes in series. And obviously we need to do one more calculation for pipes in parallel, which is your class example 27. We have kind of 10 minutes. So I think at least we can read the questions and identify all the given values so that Friday we can start from that point. Okay. So all of you have the class example 27. Okay. So let's start working on that. This is the class example 27. Can you read? Anyone can read the class example 27 so that we can identify the given values. Who will read that?
The arguments supply a new welded pipe of 2 feet diameter attached to each pipe has a filter
Thank you very much. So for this question, in between Lexington and Buena Vista, we have two reservoirs. Those are, both of them are open to atmosphere, okay? And initially there was just one pipe. I named that as existing pipe, and I will name that as pipe 1 because existing new pipe, that will take more time to write down that. So for that one, the diameter was 2.5 feet and the length of that pipe was 7 miles. Obviously, there can't be one single pipe for 7 miles. There are multiple pipes, but since they are same diameter, we can consider that as one pipe. Now, they needed more water from Lexington. So there are two options. They could replace the old pipe and use a bigger diameter pipe, but sometimes that's not the most feasible solution because maybe the pipe that is connected with lots of other pipes and maybe it's not economically feasible also. So another option can be they added one extra pipe so that it can supply more water between these two reservoirs. So now we have two pipes in between Lexington and the Buena Vista. Can you tell me how, like in which connection, which type of connection they are having, pipes in series or parallel here? They are parallel pipe system because they both are collecting water from same source. They are delivering water into the same source, right? So they are working simultaneously. That's why they are connected in parallels. So I will write down that one first. That is our first given values or first thing we need to know, that pipes are connected in parallel connection. Okay. And in between these two pipes, we have an elevation difference. And that elevation difference is what? 426 feet. Okay. Now the good thing is we have two reservoirs, both are open to atmosphere, which will give us few zero values, which will reduce the total calculation time. Okay, so and each pipe has a filter, which is that, and they have a globe valve on it. So globe valve, I didn't mention that, but it was fully open globe valve. So what we will do now, we will try to identify what are the minor losses we can have here. Okay. So for filter, KL is already given, which is 1.6. For fully open globe valve, can you go back to the table you have for minor losses and tell me what was the KL for fully open globe valve? I don't have that with me right now, but the table where you had all the steps and all the values for minor loss coefficient. Fully open globe valve. KL equals to 10. Okay, great. And we have two more sources for minor losses here. One is whenever the water or any fluid enters from a big reservoir to a small pipe, it's called flush entrance. Can you look up at your table and tell me what is the flush entrance KL? 0.5. Okay. So KL is 0.5. And we have reservoir on the other side also, where flow is just coming out from a small pipe to a huge reservoir. Can you tell me what type, like what is the exit loss or something for that? What is the KL for that one? Can I borrow that? Not that one, the minor loss coefficient one. Yeah. Okay, so for so here the discharge pipe, are you seeing there that from a small pipe it's opening to a big reservoir, and the KL is actually 1. So it's called either it's discharge pipe, or sometimes we say that exit loss. Okay. And KL is 1. So we have all of these diameter and friction factor as given values. Also, we have summation of KL will be what? 0.5, 1.6, 10, and 1. What is that number?
$13.1.
13.1. Okay. Also, we know the length of the pipe, which is 7 multiplied with 5280 feet. So what is that number?
$36,960.
Okay. This one, right? Okay. And since it's parallel connection, again, we have two exclusive equations, energy equation and the continuity equation. So I will just write down the exclusive equations. Most probably I'll be able to do that. If not, that is fine. So all of you are done with identifying all the given values here. Okay, so exclusive equations for parallel connection. First equation is Q equals to Q1 plus Q2, right? So this one is Q1, this one is Q2. That is equation number 1. And we also know the head loss at each pipe will be, let's name this reservoir at A and B. So head loss in between A and B. That is our equation 2. Okay. And for this one, we have major plus minor. This one we have major plus minor. Okay, so I will stop here. Friday. So you are taking the test on Monday, right? Okay. I will talk with section 3 also, and right after the class, I will email you about the decision, the final decision when the test will be. Okay. Thank you, class. I will see you on Friday with or without the test.